Okay, welcome back. What I want to do is to continue with AC motors, various types and utilities and applications. Okay, that's what we want to continue with, and this is going to be session 2. So you will have noticed that you carried on from session 1 and session 2, and I'm going to try and put them into their own playlist so you can look at it completely. Okay. Okay, thank you. Right, now this is just a motor that I've brought into play. Okay, and this is one of your commercial motors that you'll find in any industrial area. Okay, and it's just 0.0 kilowatts to 11 kilowatts. Okay, now it would be down for you to determine what kind of starter you would think would be applicable for this type of motor, but that's purely a question from my part. Okay, I'm just acting as agent provocateur in this case. And here's another type again, okay, purely for your information only. Okay? And this one is single phase electric motor, permanent run capacitor, 2 and 4 pole, etc. Okay. Now you'll find something about capacitor motors in one of the electrical principles lessons that I've done as well on video. Okay, so it'll be your relevance and intuition that will encourage you to go and look at that again. Okay. Anyway, AC motors, AC linear electric motors. The first linear electric motor was conceived by Wheatstone more than 100 years ago, but large air gaps and low efficiencies prevented linear electric motors from being widely used. Okay. So I was just looking for my cursor. For electric motors still have a relatively large air gaps, linear induction electric motors are increasingly chosen for material handling applications because they are quieter, more reliable and less expensive than rotary electric motors. And because linear electric motors do not drive gearboxes or rotary to linear conversion devices, they can be more efficient. So here we have information now telling you about the motors as they would be and as they may be used, and what will give you certain efficiency in certain areas. Okay. A linear electric motor is conceptually rotary electric motors feature stator cords which have been cut and unrolled. The circular stator becomes a linear stator, defining a single-sided linear induction electric motor. Okay. Now do some additional research on this for yourselves so that you can see exactly what they're trying to say. No amount of me telling you will make that difference. You need to be able to look it up and find and extract the information in addition. Okay. Likewise, if the circular stator is cut into 2 sections and flattened, the electric motor becomes a double-sided linear induction electric motor. The DLIM and SLIM both require a 2 or 3-phase stator primary winding and a flat metallic or conductive plate type armature secondary. Okay. Now here they're just telling you what they've done with the motor and what it would be look like. So you now need to look for DLIM and SLIM. in regards to types of motors. And to be sure, now again, keep in mind type of motors we are looking at. Okay. AC linear electric motors. Okay. Now, cutting and unrolling the stator leads to many other possible linear electric motor configurations. For example, tubular electric motors can be conceptually made from slim by re-rolling it in the direction of motion. Okay. Now, the electric motor pole pattern is produced by three-phase windings in alternate clockwise and counterclockwise directions around the tube. The other electric motors feature designs which are also possible, but few of them are used. There are several important differences between linear and rotary induction electric motors that bear on selection. Unlike rotary electric motors, the linear motor has a beginning and an end to its travel. First, the moving secondary material enters the primary at one end of the electric motor and exits at the opposite end. Induced currents in the secondary materials at the entry edge resist air gap flux buildup, and at the exit edge, the material retards the air gap flux decay. This results in an uneven air gap flux distribution. Such flux distribution causes little or no thrust under the first few electric motor poles at entry and a braking thrust at exit. At stall and low speeds, electric motors produce flux distribution which is not seriously distorted and is usually ignored. But dynamic compensation is required to minimize thrust roll-off at high speeds. Second, the large air gap, which is endemic in linear electric motors, effectively limits linear force. Fortunately, new pole piece electric motor designs offset the adverse air gap effect. The moving member in a linear electric motor is typically a solid conducting plate or sheet. It does not contain coils or windings. However, a linear electric motor can be constructed so the primary moves and the secondary remains stationary. And this is just what they're trying to look at. This shows how the coils are wound. Okay, and that's all I'm showing you here. It's going to how the coils are wound. Linear induction motor LIM is an alternating current asynchronous linear motor that works by the same general principle as other induction motors, but is typically designed to directly produce motion in a straight line. Here we are. AC electric motors continue. AC linear electric motors continues. Okay. Now, linear electric motors also need the secondary to be wider than the primary. The secondary should be wide enough to handle induced current with little resistive losses along the transverse edge. Such losses are known as transverse edge effects, which can reduce the electric motor's useful thrust or force. An electric motor's normal force between stator and armature in slim electric motors is perpendicular to the direction of travel. The electric motor's stator and armature are either attracted or repelled by this force. Factors that determine the electric motor's force direction include armature material, composition and thickness, stator frequency, air gap, and pole pitch. Slim motors are constructed to minimize the normal force for DLIMS, and rotary and tubular electric motors, these forces cancels out. So linear induction motors produce up to several thousand pounds of thrust. These electric motors also feature propositional accuracies of 1 microinch and velocities of 100 inch per second are possible. Feedback is usually from a linear encoder, able to provide high resolution and accuracy. Among the encoder technologies used are optical, magnetorestrictive, magnetic, and inductive. For applications involving high acceleration, the secondary normally moves over a long stationary primary. High force and short stroke applications with low repetition rates call for a moving primary and a long stationary secondary. Conversely, for long strokes and high repetition rates, a moving secondary and long stationary primary are required. Okay? And this is telling you the strokes of the machine. It's like moving a piston. Okay, that's the only way I can describe it. That comes to my mind. Okay, but when you do your additional research on this, you should therefore have a lot more information, because I didn't want to make it too, well, overcomplicated. In certain material handling and coil processing applications using linear induction electric motors, the material itself is the secondary. Okay. And I think we are going to stop here. 1 second, let me just make sure that let me see if I can finish this off directly. 1 second. Okay, yes, I think we can go on to here. Yeah, we'll. Okay, yes. We'll carry on a bit further, I think, okay? Now, for example, to handle sheet steel, overhead slim primaries induce currents in the steel and attract it to the primary. A balanced force is provided by gravity and an air bearing to levitate the sheets in air. The sheets are then propelled into piling zones without touching any surface or other object. Recent advances in power electronics, microprocessors, and electromagnetic analysis software are responsible for many new linear electric motor designs. Okay. Power electronics, okay, provide inexpensive pulse width modulation, etc. Microprocessors used for electric motor control includes 32-bit processors, okay, etc. Okay, position control is needed to compensate for electric motor magnetic saturation, etc. Okay, and that's where we're going to stop for now. Okay, so let me just go back up, make sure that we got everything on in frame. Okay. Okay, that will be it. Thank you. Yeah. Okay, and that's where we'll stop for now. Okay, that's the end of session 2. Okay, thank you.